Indicator random variables. Suppose we have an experiment with a sample space S and some event A, an event is a subset of the sample space, which has probability P of A equals P. An indicator random variable is a random variable which takes only two possible values, 0 or 1. X is equal to 1 if A occurs, 0 if A does not occur. So in the language earlier of the course, an indicator random variable is a single Bernoulli trial, or a binomial random variable, with n equals 1 and probability of success p. The probability x is equal to 1 is equal to p. Of course, the probability at 0 is therefore 1 minus p. And because it's binomial with parameters 1 and p, it has expected value p and variance p times 1 minus p. We'll use this repeatedly. Uses of indicator random variables. We often discover that indicator random variables allow us to find the means and variances of random variables when distributions for them are very difficult to obtain. On the surface, it seems hard to believe that we could get variances, for example, without knowing a distribution. But here's an example. Suppose I have n people all holding hands, creating a closed circle. This could be referred to as a ring or ring network. On a given signal, each pair of hands disjoins, in other words, they cease holding hands, with a certain probability p, independently of the other pairs of hands. This means, for example, in the graph below, there are 6 links, and links are broken independently of one another with probability p. A person I is isolated if they're holding no hands. And after the signal, let y be the number of isolated persons. Let's assume that n is equal to 6, as it is below in the graph. We're required to find the expected value of y and the variance of y. This is a problem which is amenable to the use of indicator random variables. We can break it down into small chunks. By defining xi equals 1 if person I is isolated, and 0 if person I is not isolated. Then, of course, the total number of isolated individuals, y, is x1 plus x2 up to x6. But you'll notice, for example, if the link to the left of person number 1 is broken, then it's more likely in the diagram that person number 6 is isolated as well. This implies dependence among the indicator random variables xi. And because they're not independent, the distribution of this sum is hard to obtain precisely. What do we know? Since it's an indicator random variable, the probability xi equals 1 is the probability that the link to the left of individual I and to the right are both broken. This has probability p squared. In the diagram below, the red links, when broken, indicate that person number 1 is isolated. And since we know the expected value and the variance of a indicator random variable, the expected value of xi is p squared, and the variance of xi is p squared times 1 minus p squared. This means, at the outset, that the expected value of y is easy to obtain. It's e of x1 plus e of x2 up to e of x6. In other words, it's 6 times p squared. It's important to note here that the expected value of a sum is the sum of the expected values, whether or not the random variables are dependent. However, if we want the variance of y, we need the variance of a sum. This requires the covariances between terms like xi, xj. Let's first find the expected value of x1 times x2, which is another random variable that can take only two values, 0 or 1. It's also an indicator random variable. When is x1, x2 equal to 1? This means individuals 1 and 2 are both isolated, and this only happens if the 3 links colored red in the diagram below are all broken. So this has probability p cubed. Using a standard formula for the covariance, e of x1, x2 minus e of x1 times e of x2, the covariance between x1 and x2 is p cubed minus p to the power 4. And the same argument will apply to any two adjacent individuals. The covariance between xi plus 1 is p cubed minus p to the 4th for values of I from 1 up to 5. What about the covariance between x1 and x3? Individuals 1 and individuals 3 have no links which adjoin both of them. The breakage of the two links adjoining individual 1 is independent of the possible breakage of the links adjoining individual 3. That independence means that the covariance between x1 and x3 is equal to 0. So we've established a general pattern for covariances. Covariance between xi and xj is p cubed minus p to the 4th if I and j are adjacent nodes, and otherwise covariance xi xj is equal to 0. And this allows us to compute the variance. The variance of the sum is the sum of the variances plus twice the covariances, added in this case only over adjacent pairs because non-adjacent ones contribute 0. And this works out to 6p squared times 1 minus p squared plus 2 times 6 because there are 6 adjacent pairs times the covariance of xi plus 1, which is p cubed minus p to the 4th. This can be simplified a little. That's pure algebra. Review problem. We can also use indicator random variables to confirm formulas for expected values and variances for random variables where we may have already established a formula. For example, in the case of a binomial or the hypergeometric distributions. Here's such an example. Suppose we draw a sample of little n voters without replacement from a population of capital N. We count y, the number of voters in the sample who favor the PC, which is the profound control party. That count, we already know, follows the hypergeometric distribution. Let's suppose the proportion of PC supporters in the whole population is R over capital N, which, for brevity, we'll call little p. I'm going to define some indicator random variables. Xi is 1 if the ith person that we sample favors the PC party, and 0 otherwise if they don't. What I want to do is find the expected value of the random variable y and its variance. And remember, y has a hypergeometric distribution, but I won't use the formula here for its expected value or variance. Solution. Recall the definition of the indicator random variable xi. The probability an individual favors the PC party is called little p, or r over n. So the expected value of xi is p, and the variance of xi, p times 1 minus p. Once again, however, because we're sampling without replacement, the random variables xi are not independent of one another. And the total number of PC supporters, y, is the sum of xi, I goes from 1 up to n. So, as before, the expected value of the sum is the sum of the expected values, which is n, little n, times p, or n times r over capital N. To find the variance, we're going to use a similar strategy as in the last problem. We'll note that the random variable xi times xj is again an indicator random variable. It takes values 1 or 0, and it takes the value 1 if and only if a PC supporter occurs on the ith draw sampled and on the jth draw sampled. So what's the probability xi xj equals 1? It's the probability that xi is equal to 1. That's r over n, since there are little r individuals available on the ith draw. But after drawing a PC supporter on the ith draw, there are only r minus 1 left on the jth. The probability that xj equals 1, given xi is 1, is r minus 1 over capital N minus 1. The indicator random variable xi xj is 1 with probability r over n times r minus 1 over capital N minus 1. So that gives us the expected value of xi times xj. Remember, if we know the expected value of a product, we can get the covariance, e of xi xj minus e of xi times xj. This can be simplified to p times p minus 1 over capital N minus 1. You'll note that since p is less than 1, this is a negative quantity, which means that if xi is 1, then xj is less likely to be 1. There's a negative association between those two random variables. Therefore, the variance of y is the variance of the sum, and that, as usual, can be written as the sum of the variances plus twice the covariances. N times p times 1 minus p is the sum of the variances. The number of covariance terms, I and less than j, is n choose 2, and each of those covariances is p times p minus 1 over capital N minus 1. And again, a little bit of simplification gives me the result n times p times 1 minus p, which should look familiar, times the quantity capital N minus little n divided by capital N minus 1. The first part of that expression, little n times p times 1 minus p, is familiar because that's the variance of a binomial. If sampling had been carried out with replacement, then those values xi would be independent, and that would deliver the variance of the random variable y, np times 1 minus p. What difference did it make to the variance because we sampled without replacement? We had to multiply that quantity by a fraction capital N minus little n divided by capital N minus 1. You'll notice that that's always a quantity between 0 and 1, and it's very close to 1, provided that little n is a lot smaller than capital N, provided that we sample only a small fraction of the total population. That's a modest adjustment, in general, for the fact that we sampled without replacement instead of with replacement.